Hi there! Welcome to the 44th episode of the Synth project, where we are building a synth together. After all the burden of writing the code for the software trigger, it is only right that I give it a go and see if that was worth it. After all, using a software version of the trigger will help reduce the number of components on the MIDI module and will also allow for more flexibility in future versions of the module software. Well, if it works, of course. So let's give it a try and see what happens. If it doesn't work, I will have just lost a few hours of work and I can still use the hardware version. And I will also be at peace for having tried it. But if it works, it is going to be a full gain in versatility that can become useful later. Let's begin. Here is how the schematic of the MIDI module currently looks. Op-amp U2.1 and U2.2 are currently used to generate the trigger signal starting from the available gate signal. The actual trigger signal is available on pin 4 of header 6, which is the header to which all the output elements of the front panel will be electrically attached. To be able to use the software-generated trigger, we will simply use data pin 26 on the Arduino Due, which will be connected to pin 4 of the header H6 through the logic level converter array LLC2 that has still one available converter on pins LV4 and HV4. U2.1 and U2.2, along with all the surrounding components, can be eliminated entirely. As a result of such changes, the schematic assumes this new form. Here you can see that I have eliminated the whole circuit for creating the trigger signal analogically from the gate signal. I also moved the connector toward the front panel from the center right of the picture to the upper right to make some space for the circuitry that we will design later on for the control change signals. Let's now take a look at the software changes, which are currently on version 0.5. First changes begin on line 113, where we can see the definition of two constants. The first, trigger pin, defines the data pin that will be used to output the trigger signal. The second, on line 115, defines the width of the trigger pulse in milliseconds. I defined it to be 10 milliseconds right now, and as we will see during testing on the synth, it works perfectly fine. On line 125, 126 and 127, we have the three variables that allow the trigger to be generated. The first one is a flag that, when set to 1, will tell us that the trigger has been entirely processed. The second variable is another flag that tells when a trigger needs to be generated. The last variable keeps track of the moment in time when a trigger pulse has been started. That serves to measure the length of the trigger pulse, so it can be stopped when it reaches the duration defined by trigger width. On line 209, we can see the function that actually does most of the work to generate the trigger pulses. To understand this function, we need to keep in mind that we cannot just raise the level of the signal, wait for the duration of the pulse, and then lower the signal. If we did that, we would disrupt the timing necessary to read the flow of the USB MIDI messages, as well as other internal timing needed to make the whole MIDI module work. The solution for generating the trigger pulse must therefore be a solution that does not make any pause in the code. To accomplish that, I made use of a flag that signals the need for generating a trigger signal. Such flag is tested on line 211. If a trigger is needed, we move inside the if statement and we bring the trigger signal to high. Now, to be able to lower the signal at the right time, we store the current system time on line 214. Then we lower the trigger flag, which is not needed anymore, and we also lower the flag trigger done, which we will examine in a few moments. Now, if we call this function inside the loop function of the Arduino, it will be executed over and over again, every time the loop runs from the beginning. At the next entry of this function, in the loop, we will find the trigger flag set to low, and so we will jump inside the else statement on line 220. Here we will find that the flag trigger done is set to low, and as a result we will check on line 222 if enough time has passed since the trigger was set to high. If not enough time has passed, we will just exit from the function, and at the next loop we will repeat the same test until the result is true, which means the trigger signal has been high for long enough. At that point, we lower the trigger signal and we set the trigger down flag to high. At the next execution of the function, since trigger flag will be low and trigger down will be high, we will skip all the instructions within this function, doing just nothing. Only when the trigger flag is raised again, we will repeat the whole process and we will generate a new trigger pulse. If you follow the description of this procedure, it should be clear now that in order to generate a trigger pulse, we just need to set the trigger flag to high. Function trigger handling running in the main loop will do the rest. On line 231, we have a function used to raise the flag to generate the trigger. Function fire trigger will be called in all places in the rest of the code where a trigger needs to be fired at that very moment. Calling that function will initiate the procedure for generating the trigger pulse in function trigger handling. What is left to do is therefore add such function call in every place where we need to generate a trigger, which is basically means any place where we actually play a new note. And what a better place where to do that than the function that is called to play a new note. Let's go back to line 190, where function play current note is defined. See, I have just added one single line at the end of that function, so after generating a CV for the pitch and one for the velocity, and after making sure that the gate is high, we call fire trigger to generate a trigger pulse associated with a new note being played. As simple as that. Now, in order to test all that new code, we need to rearrange the hardware of the MIDI module. We need to eliminate the existing hardware that generates the trigger from the gate signal, and we need to connect the data pin 26 to the trigger output. However, since we need a trigger with TTL level, or 5 volts, and since the Arduino produces a level high of 3.3 volt only, we need to pass the generated trigger signal through the last port still available on the logic level converter that we have previously seen in the schematic. Let's now make these changes and then let's run a few tests, first in lab and then at the Synth. First, let's remove the wire that connects the circuit to the jack socket, and also the wire that connects the gate output to the input of the trigger circuit. Then we remove the IC and all the other components and wires that make the hardware circuitry for the trigger. Removing all those elements from the breadboard leaves a lot of available space for adding the control change circuitry later on. At this point, we need to connect the data pin 26 on the Arduino Due to the input of the last logic level converter, and the output of the same logic converter to the trigger signal jack socket. All done, so now we can start running some tests. I have connected my Akai LPD8 MIDI controller to the input of the MIDI module. The trigger output is instead connected to the oscilloscope so we can visualize the trigger signal. And yes, every time I hit one of the pads of the LPD8, a little yellow dot appears on the oscilloscope screen. These dots are in fact the trigger pulses. So, at least on the bench, everything seems to work fine, and it is time to run some tests with the Synth. To test the software trigger functionality, I patched a configuration similar to the one I used to test the hardware-generated trigger. The control voltage for the pitch, that comes out of the MIDI module, goes to the input of the sample and hold module, while the sample and hold output controls the VCO. The gate and trigger signals from the MIDI module go to the gate and trigger inputs of the ADSR module, and the trigger signal goes also to the sample and hold module to control the instant where the sampling has to happen. So basically both the sample and hold module and the ADSI module receive the trigger from the MIDI module. Finally, the output of the ADSI module goes to control the VCA channel of the VCO that emits the triangular wave. With this setup, we can actually play and hear the notes only if the trigger signal works as it should. Otherwise, the ADSI module and the sample and hold unit will not be able to operate without the trigger. Let's give it a try. Let's start with a simple scale. And that seems to be fine. Let's now try with a melody. I'll use the same from last time. And that works too. Finally, we can try to see if the trigger is generated when two keys are pressed and we release the one with a lower pitch. In fact, with this configuration, only if the trigger is generated when releasing the key, we will be able to hear the other note. Here it goes. And yes, it works too, perfectly blending with the priority on low feature. It looks like the software-generated trigger works fine, and since it works, I decided to use it in place of the hardware-generated one, since it is a more reliable way of generating triggers compatible also with the note's priorities. There is one more item we need to complete before declaring the MIDI module circuit done, and that is the generation of the control voltages associated with the control change messages. That will be the subject of the next episode of the Synth project. Please make sure that you are subscribed to the channel and that you have activated the notifications. That way you won't miss the next episodes. In the meantime, I'll see you in the next video, and as usual, happy experiments!